You ever wonder how services like Netflix or Discord can handle millions, even billions of users without just completely falling over? Well, the secret isn't just buy more servers. It's an incredibly elegant architectural pattern, and it's all thanks to this one idea, something you've probably never even heard of, called consistent hashing. But you literally rely on it every single day.
Okay, so let's get into it. Put on your architect hat for a sec. Here's the deal. You've got 100 servers, and you've got a mountain of user data. Profiles, photos, messages, you name it. Your job is to figure out where to put everything, which server gets which piece of data. This is the fundamental problem of building anything that needs to scale. Now, if you're like most of us, your brain probably jumps to a pretty simple solution. You take a key, you hash it to get a random-looking number, and then you use the modulo operator. You know, hash of key modulo 100. That gives you a number from 0 to 99, and you just assign the data to that server. It seems perfect, right? It's simple, it's even, but it's also a trap. You've just designed a ticking time bomb, a system that is absolutely guaranteed to have a meltdown.
Yeah, this approach is so common and so dangerously flawed that we gotta give it a name. Let's call it the modulo hashing lie. And the chaos it creates when your system needs to change, and trust me, it always needs to change. That's what we call a reshuffle storm, and it's as bad as it sounds.
Just look at this. It lays out the disaster perfectly. On the left, everything's great. We have 4 servers, we're using hash key mod 4, and our data is spread out nicely. But then, boom, one server goes down. Look at the right. Now we only have 3 servers, so our formula has to change to hash key mod 3. And here's the killer. The result of mod 4 is almost never the same as the result of mod 3 for a given key. What does that mean? It means nearly every single piece of data across your entire system now has to be moved to a new server. It is a complete system-wide data shuffling nightmare.
And hey, don't just take my word for it. This is a classic, well-known anti-pattern. As this quote from Stanford's computer science program puts it, for any system that has to scale up or down or handle failures, this approach is a total disaster. And let's be real, that's pretty much every modern application. Okay, so if the simple, obvious solution is a total trap, what do? Well, this is where the genius comes in. The solution is an incredibly clever concept called the hash ring, and it completely flips the entire problem on its head. All right, let's build this thing in our heads, step by step. First, I want you to completely forget about your list of servers. Just throw that idea out. Instead, picture a giant circle, a continuous ring. Now, this ring isn't physical. It represents every single possible number that your hash function can spit out. It's this huge, abstract space that never, ever changes. So we've got our ring. Now where do the servers fit in? It's actually really simple. We take each server, maybe we hash its IP address or its name, and we use that same hash function to plot it onto a point on the ring. So now we've just got our servers dotted around this giant circle. And finally, we do the exact same thing for our data keys. We hash a key, find its spot on the ring, but which server actually gets it? And here is the simple, brilliant rule. From the data's position on the ring, you just start walking clockwise until you bump into the very first server you see. That's it. That's the server that owns that key. Okay, now for the moment of truth. What happens when a server dies? Let's say server S2 here goes offline. Look what happens. The keys that used to belong to S2 just keep walking clockwise. They naturally find the next server in line, which is S3. And this is the magic trick. Only the data from the failed server has to move. Everything else, all the other keys and servers, stay exactly where they are. The reshuffle storm is completely avoided. And we can actually put a number on just how much better this is. With consistent hashing, when a server is added or removed, you only have to move, on average, k divided by n keys, where k is your total number of keys and n is your number of servers. Compare that to the old way, where we had to move almost all k keys. It is a night and day difference. It's the difference between a minor, manageable hiccup and a total system meltdown. But hold on, from an architect's perspective, you know that no solution is ever truly perfect. There's always a gotcha, a subtle flaw. And even this brilliant hash ring idea has a sneaky little problem that can cause big trouble in the real world. So of course, the pattern had to evolve. So what's the problem? It's just bad luck, really. Because we're placing servers on the ring, based on their hash, just by pure chance, you could get a really uneven spread. You know, one server might get stuck with a giant chunk of the ring's real estate, while its neighbor gets just a tiny little slice. This creates massive load imbalances, what we call hotspots, where one server is getting totally overwhelmed while the others are just sitting there, bored.
So how did architects at places like Amazon solve this? Well, you can't fix bad luck, but you can roll the dice more times. And that's exactly what they did, with a brilliant refinement called virtual nodes. The idea is this. Instead of putting one physical server on the ring in one spot, you make it pretend to be hundreds of different, smaller servers. You scatter all these virtual copies of server A all over the ring.
And you can see the difference right here. On the left, that's the hotspot problem. You've got these big, lumpy, uneven partitions. But on the right, with virtual nodes, each physical server's total workload is now the sum of many tiny scattered micropartitions. The law of large numbers takes over, and the load just naturally smooths itself out. It becomes dramatically more fair and balanced.
So this combination, the hash ring plus virtual nodes, this wasn't just some clever theory from a research paper. No way. This became one of the absolute foundational building blocks for the modern, scalable internet.
And check out how fast this all happened. The core idea shows up in a research paper in 1997. Just 1 year later, Akamai is founded, and they use this exact idea to pioneer the entire content delivery network industry. Then, you fast forward to 2007, and Amazon drops their legendary Dynamo paper, which basically cemented this pattern as the gold standard for building any massive distributed database. So, who's actually using this stuff today? Oh, just about everyone. We're talking Amazon's DynamoDB, Apache Cassandra, Discord, the Akamai CDN that serves you websites, Netflix and Vimeo streaming your shows. The services you use every single day are built on this exact principle.
But the story doesn't end there. In architecture, it never really ends, right? You always have to be thinking about what's next. What are the modern variations? What are the alternatives? And most importantly, what are the critical trade-offs you have to make? For instance, what if one key becomes massively popular and threatens to overwhelm a single server anyway? Well, Google came up with an enhancement called bounded loads. It's basically a simple safety valve. Each server has a capacity limit. If a key gets assigned to a server that's already full, no big deal. The key just keeps walking clockwise around the ring to find the next server that has some space available. And you know, consistent hashing isn't the only game in town. There's an important alternative called rendezvous hashing. And this is where that architect brain has to kick in, because it's all about trade-offs. Rendezvous hashing can often give you a better, more uniform load balance by default. But consistent hashing is the absolute king when it comes to minimizing data movement when your servers are constantly being added or removed. There is no single best answer, only the best fit for your specific system's needs.
And this leaves us with one last critical and frankly kind of terrifying architectural question. Think about it. When a node fails, all of its load slams into its successor on the ring. What if that successor was already near its own capacity? This sudden shock of new traffic could cause it to fail too, passing its load plus the load it just inherited to the next node. You see where this is going, right? What stops a single, simple failure from triggering a catastrophic cascading failure that takes down your entire system? For more tech industry insights for your career or business, go to aaronwillbuilds.com or subscribe to this channel. Link in description. Join the inner loop by getting in the email list. Let's level up our business and career from an architect's perspective.